Welcome back to Physics 152 Online. This will be a rather brief video extending the ideas of standing waves on a string to treat the properties of standing waves for sound in a pipe. You can look at your textbook for a more extensive introduction to sound waves. Remember though, we've already talked about how sound waves are waves, just like any other kind of wave, except they're longitudinal waves. And so instead of the air molecules oscillating perpendicular to the direction of propagation of the wave, the air molecules, when some kind of disturbance propagates through the air, the molecules oscillate along the same direction as the propagation direction for the waves. And so as a result, when we think about a wave traveling in a column of air, such as in some kind of a pipe, the motion of the air molecules is going to be affected by the conditions at the ends of the pipe. In particular, a pipe that's closed at one end will have a rigid surface, and at that point the air molecules will not be able to move. So if a sound wave travels down from an open end of a pipe down toward the closed end at the opposite end, those air molecules at that closed end will not be able to move, and therefore there will always be a node that's in that location. Conversely, at an open end of a pipe, the air molecules are unconstrained, and so the motion that they have at the open end will be characterized by an antinode. And that's actually a small simplification, because the true antinode for a standing wave in a pipe is actually just a little bit outside the open end of a pipe, but it's awfully close to the end, and so for simplification we'll just assume that the antinode is at the end. Now you can also think of sound waves, and you'll see this in our textbook, described in terms of the variations of pressure. And so for the treatment that I'm going to show you today, I will not be talking about sound wave as a pressure variation, but rather as in terms of the displacements of the air molecules. So just as in the case of a stretched string, we can sketch standing wave patterns and then determine the wavelength and the frequency for each one of those patterns. But first we've got to consider those boundary conditions like I was just describing. So to summarize, if you have, and just to back up for a second, the reason you get standing waves inside a pipe, like an organ pipe, is because you have a wave that propagates down the length of the pipe that then experiences superposition with the wave that's reflected from the end of the pipe. And so you get two waves moving in opposite directions through the same medium, and when the conditions are just right, then a standing wave is what results. So to summarize, the closed end of the pipe is where the air molecules cannot move at all because of the rigid boundary. That produces a node for the sound wave, and at the open end, that is a position of an antinode. So here is an example of a pipe open at one end and closed at the other end. And so if we start at the closed end and realize there has to be a node there, one possibility for there to be an antinode at the other end is shown here. This is actually not the lowest frequency that's possible, but it is one possible kind of wave. Now notice here, this is a little bit of an oversimplification to this picture, because the sound wave is actually composed of air molecules that move horizontally. They move along the length of the pipe, which is the direction of propagation of these waves. But in order to show it in a simplified picture, I'm going to draw these wave patterns as if we really had something more like a wave on a string. So the vertical direction, I'm going to draw it as if that's the direction of disturbance of the air molecules. And so the dotted line would represent the equilibrium position, thinking of this as a string. So here you'll see a node at the end, like I said, another node at the point indicated by the arrow, and then at the open end you'd have an antinode, and of course another antinode over here inside the pipe. So this is just a simple case where we now could figure out the wavelength of this particular standing wave by realizing that the length is equal to 3/4 of a complete wavelength. To make a complete wavelength, the wave would have to go a little bit further outside of the pipe. And so the relationship between length and wavelength is given by L equals 3/4 the wavelength. So if we solve that for the wavelength, we see that the wavelength is 4/3 times the length of the pipe. And of course, sound waves obey the same kind of relationship that all waves do. The frequency is equal to the velocity divided by the wavelength. So substituting for the wavelength, frequency is 3v over 4L. And of course, this is just an example. So the thing about pipes is that the boundary conditions are a little bit more complicated than you have for a stretched string. For a wave on a string that's stretched at both ends, each end has the same kind of boundary condition, and if the string is fixed, that has to be a node. Well, with pipes like organ pipes or flutes or other kinds of woodwind instruments, we can have a pipe that's open at both ends, or, as we just showed on the previous slide, a pipe that's only open at one end. And these two kinds of combinations of boundary conditions produce standing waves that are a little bit different from each other. So if we look at the pipe that's open at both ends, here's the lowest frequency that you can have, where you have a wave pattern where there's an antinode at each end. So the only way for that to happen is for there to be a node right in the middle. So in this case, we can see that the length of the pipe being L, the wavelength for this standing wave pattern would have to be 2L, because you'd have to go another distance equal to the length of the pipe to come back to the same point on the wave. And that produces a frequency, we'll call it F1, which is V over 2L. And of course, that's the first harmonic, or the fundamental frequency for a standing sound wave in this pipe. The next higher frequency pattern would be one that would introduce another node. So in the first case we had one node at the center. Now imagine two nodes inside the pipe, equally spaced, that break the pipe up into different length segments. And so in this case we have to have antinode at the ends, again, the open ends, and then nodes in between. So in this case you can see that the length of the pipe is one complete wavelength. So the wavelength is equal to L. F2 is V over the wavelength, which is V over L, and notice that that's just twice the fundamental frequency, or twice the first harmonic frequency. So we can summarize, if we were to do this over and over and over again, we would see that the allowed frequencies, the normal mode frequencies, would be F1, 2F1, 3F1, and so on. And this is similar to what we found for a stretched string, where all of the harmonic frequencies are present. The first, the second, the third, and so on. Let's consider, though, by contrast, what happens for a pipe that's open at one end and closed at the other end. Here is the lowest frequency possible. So for a node at the closed end and then an antinode at the open end, we get this pattern, and inspection of this shows that the wavelength would actually be equal to 4 times the length of the pipe. This is only 1/4 of a wavelength that we show here in the sketch. And so as a result, the frequency F1 is V over 4L. And then if we're going to introduce another node into this pattern, for the next higher frequency, we would have a node right here near the open end, so that you'd still get an antinode at the open end. And careful inspection of this shows that the wavelength is equal to 4/3 times the length of the pipe. If we solve for the frequency, we get 3V over 4L. And notice this. This is where it gets interesting, because that is 3 times the lowest frequency. So even though one might think of this as F2 because it's the second highest frequency that you can have, it's not equal to twice the first harmonic, and in fact it's actually the third harmonic frequency, because it's the third multiple of the lowest frequency. So in this case, what we see, the allowed frequencies for a pipe that's open at one end and closed at the other, are the odd harmonics. So it turns out that the even harmonics are missing, and as a result, these kinds of pipes are going to sound different when we excite standing waves inside them. Again, what happens in a real life instrument is when air is blown across the open end, we don't just generate one of these standing wave patterns, but actually a mixture of them, a mixture of different harmonic frequencies. And so the sound that we hear is a combination, depending on which ones are excited most strongly, it's a combination of all of the possible frequencies that match the standing wave condition for that pipe. So pipes that are open at both ends and pipes that are the same length but open only at one end will definitely sound different from one another, because there will be a different combination of the harmonic frequencies when we excite those tones. So a little bit more about this we'll go into detail in class, but hopefully this has been a good introduction to standing waves, standing sound waves in pipes. I'll see you in class.